Okay, good morning, everybody. We are going to continue with the session of this third day of the workshop, Topological Quantum Matter, with the contribution by Professor Babak.
Thank you. Is this working? Okay. Good morning, everyone. Thanks again for having me here and for being here. I need to use this. Okay. So I will continue with the topic that I started in lecture 1 with topology and driven systems, but hopefully about halfway through the lecture today, I will also talk about some aspects of topology and Lorentz violation that connect condensed matter and high energy physics, more in line with the spirit of the workshop here. Let's see if I can move this. Okay, so this is what we did on the first day. So I I gave an introduction to topological phases, especially in periodically driven quantum systems. I gave you some examples of these topological phases and some aspects of topology, especially as you go to lower frequency. I talked about a theoretical suggestion of Floquet engineering in graphene. So I will continue with that a little bit. So I will talk about some other aspects of graphene under circular polarized light. And then, as I said, I will switch gears a little bit and talk about Lorentz violation connections between condensed matter and fundamental physics. So this is where we were with graphene under circular polarized light. These were suggested theoretically back in 2008, 2009. And they were not observed immediately. The experiments in graphene are actually quite hard. In terms of experiments, there are a number of experiments since then that have come online. Most recently, actually, just a few months ago, also in graphene. But initially, in materials, the first indication of these sort of states came from surfaces of topological insulators. So this is bismuth selenide. And the experiment that was done here was angle-resolved photoemission spectroscopy that gives access to the energy bands. And what they added here was time resolution. So basically, they added a pump. That would be the drive on the system. And then the ARPES probe will come at some time after that, right? So that time delay was crucial to actually see this. So they can also actually do the opposite order, right? If you first do the probing and then drive, then you don't expect to see any sort of Floquet physics. And this is what they saw. These are ARPES. This is the ARPES signal. And it's, as usual with ARPES, it's kind of hard to see exactly on these graphs. You can see indications, but there is actually some quantitative analysis that you can do. That's what gives rise to these dashed lines. And they could extract the gap that opens as a result of the laser drive. Now, these drives are actually I think they were in the terahertz regime. And the gaps match the predicted theoretical value. Some years later, about 6, 7 years later, another experiment, this is a transport experiment, was done in Germany. And here, this is sort of a non-local transport measurement. The driving is happening here in the sample, graphene. And the idea is that if this really creates a topological phase, then it has to have the chiral H states. And those chiral H states will have this is a lead here, will continue in this direction. And then you can expect to measure a current farther away from the sample over here. So to measure this current, actually, it's not an easy task. You have to do some additional probe here. And the main thing is that because of all the background and so on, you may not be able to detect the current that comes from the edge states directly. So what they did was to switch the helicity of the circular polarized light here, and that would control the sense in which the time reversal is broken. And so that would control the direction of the chiral edge modes here. And then they took the difference. So this difference shows up in the signal, and this is some time basically after the laser is shown there. And they could confirm that the difference actually shows up as non-zero in this signal. So the difference should, in principle, or in the idea is that if you take the difference, all the background should cancel out. All right, so as I said, there are a number of other experiments, especially in other systems. The first indication actually of this sort of Floquet topology came from photonic devices, where you can, when you can create some coupling between different fibers and create lattices of these optical fibers. But in materials, as I said, this has been a little bit harder. The main drawback, of course, in materials is as you drive the system, especially with intense lasers, you create a lot of heating. And so that can spoil the effect. So that's an outstanding problem in the field that needs to be addressed. And these sort of signals are typically pretty short-lived because the intensity of the laser means that the laser is created in pulses, and those pulses last only a short time. So there are also questions about, for example, is this really the steady-state Floquet that theoretically you would like to have, because the time is very short. Okay, so, I'm a theorist, so we can just march ahead, and as was mentioned in some other talks, we can imagine some additional ways of control. So one of the main features of this sort of Floquet phenomenology is that you gain a lot of control through the parameters of the drive. You can control, of course, the intensity, you can control the frequency, you can even control the shape of the drive by adding various harmonics, and various effects due to these parameters have been explored. So something that I was interested in for a while was to see if we can actually use the orbital angular momentum of light as also a control knob. And so that brings us to what is known as twisted light. So twisted light has a wavefront that kind of looks like this. Let's say the vector potential has this form. We have, as usual, you have a polarization vector, you have the frequency, and but the spatial profile of the vector potential now has this phase dependence that carries the orbital angular momentum, not just sort of the spin angular momentum. And due to that, actually, this radial profile of the beam also has a vortex profile. This is very much like a vortex. Actually, I didn't put a diagram on the board, on the slide, but I can maybe draw something here. So let's say if you have linear polarized light, then the electric field is going back and forth along some direction. Circular polarized light means that if I sit in this plane, then this is rotating, but still at any given time, it would be in some particular direction. With orbital angular momentum, let's say m equal 1. This is m equals 0. Let's say circular polarization. I don't know, it's right-handed. This is linear polarization. At a given time, my field would look like this, and as a result, it actually has to vanish at the core. And now you can have also on top of this the polarization. If you have linear polarization, it means that everything basically at any given point goes along that line. So this kind of goes in and out like this. If you have circular polarization, it means at any point these fields will be circling around like a clock, right? So you will have these clocks that are oriented at different times, and they're circling, they're rotating at the frequency of the beam. Okay, so this kind of case of linear polarization was considered in the literature before. Now the thing is that without orbital angular momentum, you need circular polarization to break time reversal symmetry. So that was important to give you the gap and the Chern number. With linear polarization, you would not get that, right? So you can open up a gap in different directions, but the spectrum still remains gapless. The gap is closed in the direction of the polarization, and you don't break time reversal symmetry. But with orbital angular momentum being non-zero, you already break time reversal symmetry with the orbital angular momentum, and so even linear polarized light would have a time reversal broken character, and possibly give rise to a Chern insulator. And indeed, that's what these people found. They actually developed or looked at some kind of local Chern marker, because the vortex profile of the light means that the translational symmetry here is broken, so you cannot employ the usual band structure calculation or momentum space calculation of the Chern number. And what they found was that indeed, there is some non-zero value of that local Chern marker. And in particular, at the edge, you will see these states that would indicate that there is some chiral edge mode. Okay. So in this case, it seems that the entire system can become a Chern insulator. Now, with circular polarization, the situation is a little bit different. So I remind you again, without the angular momentum, without the orbital angular momentum, this is uniform field in the sample. And so you could employ, the translational symmetry is not broken. You can employ momentum space calculations. And this is what we had before. This is the spectrum as a function of the frequency, frequency decreasing in this direction. I don't see the label. I think I removed it by mistake. And these are the sort of various topological invariants indicating whether there is, if you open the system, you have open boundary condition, whether there is bound states in this gap or the gap above there. Okay? So one thing that immediately is sort of tempting to think is that if I add the orbital angular momentum, because of the vortex profile, the intensity of the light is actually varying in the sample. So it should be possible that maybe I sample various topological phases in the same sample instead of having just one of them. So that was the question we asked ourselves. Is it possible to get multiple flow-K topological phases in the same sample at a given frequency and sort of overall intensity of the beam? And to answer this question, theoretically, as I said, the translational symmetry is broken. But if we assume that the wavelength of the light is much larger than the lattice spacing, then I can treat the position in the Hamiltonian as basically a parameter. So I employ this sort of semi-classical approximation where the crystal momentum and the position both appear as parameters. Okay? And of course, there's time. Then we can calculate quasi-energy spectrum, and that becomes a function of both momentum and, let's say in this case, considering a cylindrical beam, the radial coordinate. Okay? So if there are multiple phases, that means that basically this part of the sample here has one topological invariant, then that topological invariant changes, you get some kind of ring around it, and so on and so forth, until you get to the edges of the sample. By the way, if anything doesn't make sense or there's a question, please do stop me. I don't mind. All right, so analytically, this is something that you can extend from the previous work. As I said in the past, you can employ this approximation at the high symmetry points, for example, the gamma point, the K point, up to the lowest order in the Fourier expansion. You get some Bessel function. At one point you have J0, at the J1. And the argument here would be, if there was no orbital angular momentum, there would be just this parameter that relates to the intensity of the beam. But now we have a dependence on R appearing through the vortex profile function. Okay, so taking a form of the vortex profile, so for within the core, it would be that goes like R to the power M. You can then find whether you get gap closings, and indeed, as a function of the radial coordinate, you can see, for example, the gamma point is this blue line is closing the gap here at multiple points. This plot is taken for a particular set of values of frequencies and intensities, orbital angular momentum m equal 1, such that you can also see that the k point and the gamma point have a gap closing at the same radial position, so that so they can actually coincide in space. Okay. Now, if you do a more accurate numerical calculation, the bands change a little bit because, as I said, this is the lowest order in the Fourier expansion. But this feature that you can, for example, get coincident gap closings in space still is there. That can be obtained. Okay. So what is happening? One way to look at this plot is to recognize, what is happening basically in the sample is that, for example, in this region, in the core of the beam, you have some state that might have edge states or not, but then after the gap closing at point A or B or other points, you're actually changing that state. You go into a different topological phase because of this gap closing. As I said, there's this coincident point, so these can happen at the same point in space. And as before, there are some avoided crossings. So this one actually turns out, so if you do this naively, this would be a crossing, and then you go to the higher order in the expansion, you find that these are actually avoided. So these we can predict analytically because of the symmetries at these symmetries of the Hamiltonian at these high symmetry points. All right. We can do a little bit more analytically. So near these gap closings, I showed you before that you can do an effective theory. You can take the two states that are crossing and then do an expansion around that, and you find an effective Hamiltonian. And if you do that here, basically you get a two-state effective Hamiltonian, which would be some form like this. You can calculate this d and mu analytically, and then from those you can of course, at the gap closing, this effective mass would have to go to 0. And then you can access the wave functions this way, right? So you can find the wave functions as superpositions of these two. And that gives you access to the structure of the wave function, and you can do more analysis based on that if you're interested in transport, something I showed before, or other aspects of the system. Okay, so I think I talked about this. Right. So let me show you now. So this is all analytical work. We also did some numerical work. My student did all this. Actually, a lot of the analytical calculation also he did by himself. So he should get the real credit here. But what he found was that, of course, in the finite system, you don't get exact gap closing because you only sample a finite number of points in the spectrum. But if you sit close, for example, to the edge of the Floquet zone, then you have states that are pretty close, so you can examine them. And so you picked these are numbered here for this particular value. And what we expected analytically for these values was that there would be a gap closing at the radius that is shown with this dashed circle here. And indeed, these are numerical plots. The rest of this is numerical. And you can see that these wave functions are concentrated around this. Now, there's some orbital structure that we cannot calculate analytically. Yes, question?
Maybe a clarification. So on the previous slide, you have expressions in terms of K and R.
Mm-hmm.
It looks like a semi-classical
Yes, yes.
way to go. And then here, I think I am seeing the honeycomb. So I can
Yes.
see the size of the system.
Yes, so this is the numerical calculation. So the question was, in the previous slide we had K and R, so in the semi-classical approach. So that's analytical calculation. Here in the numerical calculation there is a sample. So that sample is basically sort of a disk. Of course it's graphene, so it's jagged around the edges. But that's the sample size. And this dashed line is the radius that is calculated analytically. For the given parameters that we chose, we expected to get a gap closing at the gamma point at that radius. So I'm basically now giving numerical evidence that this is happening. And so these states are localized around that circle. But again, this is real space numerical calculation, so we don't know if this is a gamma point or if there is a gamma point, right? But one thing that you can do, even numerically, is to just take the states and do a Fourier transform, a finite Fourier transform. And these hexagons are the sort of the indication of the Brillouin zone of the graphene sample, right? Okay. So then the Fourier transform is calculated numerically, and this is shown as the density of the Fourier transform at A sublattice or B sublattice, so if you sample only those. And these are around the gamma point, so that's again consistent with the expectation. Now, it doesn't prove that this is a gamma point because there is no gamma point in the finite system, but it's an indication that the analytical predictions are at least not completely off. All right, here's another case. Now these parameters are chosen so that we can simulate these in a finite system with 1,000 sites or something like that. They're not truly something that you can do experimentally necessarily. These are, for example, this is a pretty large value. Okay? But for this value, we expected to get a gap closing at the K point. And again, the calculated analytical value of where the gap closing happens in space is shown here. And indeed, we found numerically that there are states here that are marked 1 through 9 that are concentrated around that. Here you also see some other states. So these are the red here. And these are actually at the edges of the sample if you look at them. I'm not showing them here, but if you look at the wave functions, they are actually located at the edges of the sample. And as I said, again, because these all happen in the same sample, when you look at the energy spectrum, you just see a bunch of states. And so you have to do some analysis to see where they come from and what they relate to. And again, the Fourier transform now is more concentrated around the K point. Again, this is a numerical calculation. There isn't really a Brillouin zone here. But if you do the numerical Fourier transform of the real space wave function, you see that it's more concentrated around the K points. All right. So, as I said, these are states that you can tune. So now you have tunability with alpha. You have tunability with omega. Of course, you can change the orbital angular frequency, orbital angular momentum. And one thing that is interesting is that the value of the radius is actually not set by itself. If you remember the argument, for example, in the analytical calculation, the argument of the Bessel function was something like alpha times this vortex profile f. So when I want to find what is RC, where the gap closing happens in the sample, I pick my whatever alpha I chose, and then I find RC from the value of that argument. This means that even by fixing omega, the frequency of the light, if I change the alpha, I can tune RC itself, where it happens, such that alpha times f of RC is the same value that it needs to be for the gap closing to happen. So this means that by tuning the intensity of the laser at a fixed frequency, you can actually control where these gap closing happen in space. And if you're at the value where you have coincident gap closing at, say, gamma and k point, you can actually tune both of them in and out, and put them wherever you need them to be. So this gives you some additional control. I think what I'm showing here is a case where we actually show this tunability numerically again. So you see that the frequency is the same. I'm changing alpha from 3 to 6, and that results in a change in RC. So this is what I showed before at the gamma point, and RC is now tighter or smaller, so the states are more tightly spaced, closer to the center of the vortex. So we discussed this a little bit more in the paper, where the ability to tune actually where the gap closings happen in the sample can, in principle, give you some additional ways of superposing the states. So, yes?
Another question, I'll speak out loud.
Okay, yep.
So the analytical model was considered at the capital K point?
Yes.
I guess the question is, when you go to the numerical model, you're actually having solutions on both K and K prime?
Yes, you have everything, because we just take the tight binding model of the lattice. We add the vector potential, so that's now a time dependent. So there is no approximation, semi-classical or otherwise, in the numerical calculation. So it's all the tight binding model plus the vector potential, and then we do the flow K.
So the question is, on the Fourier transforms that you had on previous slides,
Yes.
it kind of looked like the distribution was most located on 3 points in the hexagon.
In here?
Yeah, well, in some cases.
Yeah.
I guess my question is how you are connecting, the numerical model to both values.
Of K and K prime. Yes, okay, so this actually does not, the analytical calculation does not distinguish between K and K prime. Let me think about that. So the only difference is that, the helicity actually switches when you go from K to K prime. And I think, well, okay, so the form of the wave function changes, the energies are the same. The form of the wave function changes, and if you go from m equal 1 to m equal minus 1, so the other, or the opposite way, then the two K and K prime will switch. Yeah. Okay. Yes. So this is actually something that we were interested in for a long time. In some previous work, we had studied how you can address different values in graphene by shaping the drive. So you add some other harmonics, like fourth harmonic or third harmonic or something. It turns out that you can address you can change the quasi-energy spectrum, basically break the inversion symmetry of the lattice. But that would only address the gaps, right? You cannot superpose K and K prime, for example. So here, there's an additional control because you can control where these rings are happening. So if you had, for example, a sample size of a certain size, and you have a coincident gamma and K point ring, these are gapless points at those points, you can bring them close to the edge, and the edge acts as a potential that can scatter between K and gamma or K and K prime and so on, depending on the form of the potential on the lattice scale. And this means that you basically add a matrix element to the effective Hamiltonian that can scatter you from K to gamma. And if you control the time and the place where this happens, then you can imagine doing some quantum state engineering as well. All right. Yes, I think that's the last point there. Okay, so I'm gonna, let's see, I have about 30 minutes, is that right? Okay. Maybe I'll go a little bit more quickly in this site. So going with the theme of sort of engineering and control, of course, this is now a very big deal in condensed matter, where you can basically take layered materials, whereas before you were growing in layers, but now you can take them and twist them around. And that angle of twist actually gives you a control of the electronic states. So this is a depiction of that. I think we saw this in one of the talks as well. Here's a Hamiltonian where you have sort of the Dirac Hamiltonian, if you will, for each sheet of graphene. And then there is a tunneling between the two sheets that depends on, this whole Hamiltonian depends on the angle. So I won't go through the details of how to do this. Let me show you this, this diagram. So what happens when you twist is that each Dirac cone of each layer is now displaced with respect to each other as a function of the angle. The distance in K space depends on that angle. If there was no tunneling between the two layers, then this would be the band structure. But now the tunneling, what it does is that it mixes these states. And in fact, it takes this band and basically creates a band repulsion between this branch and the branch above it. And that leads to lowering the energy here. Okay? So now, if this distance, because of the linear spectrum in graphene, basically this energy here is Fermi velocity times this K. If that is comparable to the tunneling amplitude between the two layers, you might expect something drastic to happen. These energy bands should change a lot. And indeed, at that scale, what Bistricher and McDonald found now about 14 years ago was that the bands can become completely flat, or almost completely flat. The bandwidth here could be in the order of micro electron volt. Okay? I think what really, yes? No, A and B are the sublattices of graphene. Yeah, so in this approximation, so when you have the two layers, the tunneling can happen between A and A, or A and B, between the two layers. From A to one layer to A to the other layer, or A from one layer to B to the other layer. Two tunnelings here, yeah. In this model here, in Bistricher-McDonald model, they were taken to be the same. So this ratio was 1. Later on, I want to match the sort of experimental values that people found later. It turns out that the experimental value is closer to 0.8. Okay, and this value alpha here actually relates to the angle, because the K theta depends on the angle. And so this value relates to a particular angle, which is about 1 degree, 1.1 degree, yeah. Known as the magic angle, where the flattening happens. Okay, so I won't go through this very detailed. You've already seen chart number multiple times in this workshop. And so what we wanted to see was what happens if you have, again, the same system, twisted bilayer graphene with circular polarized light. So what this does is that it changes the Hamiltonian in each layer by adding the vector potential. The rest of the Hamiltonian is the same. Okay? So now we do analysis. And this is something I'm actually go into very carefully. At very high frequency, the Fouquet analysis is basically taking an average of the Hamiltonian, because the terms in the Hamiltonian that are oscillating fast, you can average out. And then you can build up a perturbation on top of that due to the drive. And one way to think about that is that your Fourier components of the Hamiltonian are basically describing tunneling between, having, say, 0 photons or 1 photon, right? So that would be the first Fourier component. And of course, you can have, so that basically adds a photon. That's this H1. H minus 1 brings back the state to, by removing the photon. And this perturbation theory here is just usual perturbation theory that you can basically say second order perturbation theory. So if I start at a state with no photons, I can add a photon, go to a virtual state, and then come back here, right? And the energy difference is the energy of the photon, so that's omega. And so the Hamiltonian that describes that, or the additional part of the Hamiltonian describes that, is given by this. And you can do the same thing in graphene and find that this is the value of the gap that you get there. These Fourier components are proportional to a vector potential, so this is a squared divided by omega. So a very similar thing happens here, except now you have 2 layers, so you have to do a little bit more careful analysis of the symmetries and so on. But at the end of the day, what we found was that so again, this direction is high frequency. So this here would be just the usual spectrum of twisted bilayer graphene. You have very flat band showing here. There is a gap that separates that from the other bands on top of it. As you lower the frequency, what happens is that the bands here actually are separating. Now there are 2 flat bands. Yes?
Just one question. Is this twisted system with twisted light?
No, no twisted light. Just a uniform circular polarized light. Yeah, the twist is in space now. Yeah. Yeah. Right, and the result of this is that the 2 bands that were flat, so remember there is one band coming from the positive side of the energy and the other one from the negative, they are actually now separated. Okay, so there is a gap develops between them, and that has to do with the time reversal breaking due to the circular polarized light that is added. So we expect that these bands actually now have non-zero Chern number. Okay, as you can see from this diagram, this is a numerical calculation. This is sort of the UV range of the frequency. These are still pretty flat, maybe not as flat as down here, but the band width of these are more or less comparable to the gap between them. So they're pretty flat. They have non-zero Chern number, and this would be a great place to look for correlated physics, topological physics, strongly correlated topological physics. In particular, we were hoping to find fractional Chern insulators. Okay, so maybe in the interest of time, I actually move from this diagram. And so I'll stop here. If there's any questions about the previous material, I can answer, because I'm going to shift gears just a little bit. Okay. So the rest of the lecture is about the sort of these connection, and this is some collaboration with our high energy colleagues at IU, especially Alan Kostelecki, Ralph Leonard, I think both of whom have connections with this institution. And the work was supported through the IU Center for Space-Time Symmetries and Department of Energy. All right, so what about this connection? Of course, Lorentz symmetry is broken in almost anything we do in condensed matter already. The energy bands don't have Lorentz symmetry, right? However, as you've seen multiple times now, in systems like graphene, for example, you have an emergent Lorentz symmetry, right? Just around the Dirac cone. Of course, Lorentz symmetry eventually is broken as you go higher in energy because there are higher order corrections to these, this nice linear dispersion. Nevertheless, this emergent Lorentz symmetry actually plays an important role in the properties of the system, and it appears in many different systems, so not just graphene. In cuprates, for example, there is a Fermi surface, and that Fermi surface doesn't have any Lorentz symmetry, but order parameter has a D-wave orbital character, which means that it has places on the Fermi surface that it goes So just around the stations, linearize the spectrum. Very similar phenomenology happens as in cuprates compared to graphene, except that in that case the excitations are Bogolian on top of the ground state. Yeah. So the low energy theory governs this long wavelength sort of universal physics, especially if you're interested in critical of the system and so on. There is a caveat, of course, you have to be careful, as a few times, that, for example, in graphene, there are two valleys, and the low energy physics will know about these valleys, about these zones, but not about how or communicating with each other through the band, right? So you have to be careful with that structure, especially if there is an anomaly. All right, so that's one example. Of course, we've seen this example at length, especially in Professor Shevkovy's lectures. So I'm going to use this as a Dirac Hamiltonian to various gauge fields. So this is the usual Dirac semi-metal. You can add a mass that describes in the condensed matter side some kind of ordered state depending on the structure of the mass. Break Lorentz symmetry here in a very subtle way, in fact, by not opening up a gap or going to high energy or anything like that, but by adding this chiral gauge field or axial gauge field, B, which separates the components of the Dirac spinner. So you still have a gapless spectrum, but now basically you're breaking time reversal symmetry. Let's say if this B is completely spatial, and this also breaks Lorentz symmetry. Okay. Yes.
In high energy physics, when you have Lorentz symmetry, there is one benefit that elementary particles like fermions and massless. But this is not the case because those photons would not be even propagating in the same system. Like usually they escape in three-dimensional space if you're talking about graphene.
Right. Yeah, so depending on the dimensionality, so here the dimensionality is actually 3D, right? So, but in graphene, you're right. So the actual light that is, carried carried by photons, that has a speed of light, right?
In 3D, they're not moving at the same speed.
Same speed, that's right. So there is a Fermi velocity here, that's right, which has this slope. So I agree with that.
Symmetry because the bosons are propagating with a very different speed photons than the fermions of matter.
Yes. So that would be. So let's say if this A is the photon vector potential, then it has its own dynamics, which is the speed of light in the electrodynamics, right? Yes.
The Lorentz symmetry is explicitly broken just by that speed.
Oh, you mean by the Fermi velocity being different? Yes. Yes. So yes, exactly. So this is the Lorentz symmetry in the wire semi-metal is not the fundamental Lorentz symmetry with the speed of light. There is an emergent Lorentz symmetry in the fermion, dispersion, but that relates to the Fermi velocity. That's kind of one of the, yes, that's right. Okay. So that's condensed matter side. On the fundamental side, you're interested in breaking of Lorentz symmetry for various reasons. One reason is just to test Lorentz symmetry itself, how accurate it is. And this sort of line of thought can be extended. So I showed how you can add a B term and break Lorentz symmetry and so on. But you can actually, I'm missing something here. It's not showing. Let me see if it's a slide's got. One of my slides is not here. Okay, let's see. Okay, let me show this first. I don't know why I put it there. In my mind, I was going to talk about this slide. So let me talk about it, and then I'll go back. Right, so you can break Lorentz symmetry, say on the fundamental side, in fundamental physics, in many other ways. So now it's just adding the B term, so the B, so that appears as something that looks like a mass term, actually. Because it's a term that connects, to no derivative. But you can also change, for example, the sort of the gamma matrix structure that comes with the derivative. And so this would be, if I have just the gamma mu here and the m, this would be Lorentz invariant. But by adding b or c or all these other coefficients, you can also break Lorentz symmetry. So these break also some discrete symmetries in different ways. Then you can ask, what is the signature of this in some observable? And if you are able to perform that experiment, then you place some bounds on any of these coefficients. So this is a program that has been carried out for many years now. There are very stringent bounds on these coefficients on the fundamental side. Okay, so let me see if I can go back. All right, now if you take that sort of, the big classification of Lorentz symmetry, then you can connect to a lattice model immediately and ask if there is any sort of material that realizes it. And the B term, of course, is well known. So for example, if you add the B term, here is the B term here. And this is the other side. And you can immediately do some kind of Wilson map from the field theory to a lattice model. So this is the Wilson map that takes you from, let's say, k to sine k. The mass is replaced with this, and so on and so forth, to give you sort of the right number of species of Dirac fermions on the lattice. Then you sort of turn the wheel and find the energy spectrum, and so on and so forth. So this is something that was shown before, that adding a spatial B term, for example, breaks time reversal symmetry, and so it leads to a quantity of Chern number. So if I go from one side of my Brillouin zone and the lattice to the other side, my Chern number actually evolves and becomes non-zero in some portion, which is between the two nodes. And what that means is that in this region here, I should expect to get chiral edge modes because of the non-zero Chern number in the surfaces that are on top, let's say here on top and the bottom. And indeed, if you look at, again, the lattice model, you can open the boundaries and do the calculation with open boundary conditions. And you see that gap is closed now with open boundary conditions. You can do some analysis of these states, so see what these, what states are closing the gap. So this is periodic boundary condition. And if I want to know if these states are extended or bound, one way to do that is to calculate what is known as the inverse participation ratio, as shown here, for extended states. So basically this goes inversely with sort of the support of the wave function. If the wave function is extended, that would be proportional to the sort of volume or the area of, depending on the dimensionality. And if it's localized, then it would have a finite support, so it should be a constant, which does not scale in size. So if you go to a large enough system, you can tell apart extended states and bound states. So these plots here are, again, energy spectra, periodic boundary condition here, and the coloring shows the value of the IPR. So here, basically, all of the states are some very small number, 1 over some volume, which is very close to 0. Okay. If I go to open boundary condition, exactly where the gap is closed, I will see that there are states that have much higher values of the IPR. And that's an indication that these states are bound, okay? Even without looking at the wave function directly, because of course the wave function you would have to plot or analyze on its own. Okay, you can also look at where these are located. So that's just taking the average position. And if you calculate that again in periodic boundary condition, these are all extended close to the value is close to 1/2. With open boundary condition, you get one side or the other, depending on which side of the spectrum you're at. Okay, so these are bound states. These are known as Fermi arcs. If you do some more analytical calculation, it's possible to actually find all of these states that are shown here. So these are states that are localized on the surface, and they have this very peculiar dispersion. If you call this a dispersion, there are missing parts, right? So they end abruptly. And so if I have a particular energy that I'm interested in, I go and cut this, and I find this line, for example, and that line is ending right here. Okay, so this is another indication of this topology in the bulk. All right, so I already showed this slide. Let's look at a different term, and again ask if there is some sort of topology here. Now again, in fundamental side, because of these astringent bounds, we expect all of these coefficients to be small. As far as we know, Lorentz symmetry is not broken. Which means that you can do perturbation calculations and things of that sort. We'll come back to that in a minute. But if you take the G term, you can do, again, a similar game. You can find the energy spectrum and so on. In this case, the G term is actually a huge tensor. You have to make some, you have to find your way through the structure of this tensor. And it turns out that one way actually to make this Hamiltonian description work is to set some of the coefficients to 0, and then you end up with basically two symmetric traceless matrices that are each described by just 3 parameters. And depending on which one you have, you can maybe set one to 0 and study the other one. So this is one case. And that's comparable in the structure of the term with the special B term.
Sorry.
Yes?
Was the G term in the generalized gamma matrix?
Yes. Yes. Yeah, it's a gamma matrix, and it comes with the commutators of gammas. Yeah. Mm-hmm. And again, I'm showing here, so what is happening with the G term is that it actually, because it's in the coefficient of the derivative, it doesn't actually like move the Dirac points or anything like that. It creates this sort of ripples. That's how it's breaking the Lorentz symmetry. And if you make it larger and larger, if you were able to make this larger, maybe in a material, you can end up with a spectrum that looks like this. So now the bands that are positive energy, negative energy are actually intersecting at these lines, okay? So here maybe you see it better. This is 0 mass, so the original Dirac point is here, but now you have a Dirac line that looks like this, I don't know, infinity shape or butterfly. Yes, 5 minutes? Okay, good. If you have a mass term, of course, the Dirac point itself is gapped out, and, but you end up still with these loops, okay? So maybe I will just show this for this part. The topological invariant here, it turns out, because of the structure of the Hamiltonian, there's a so-called sublattice symmetry, or it's also known as a chiral symmetry. It's a little bit different from chirality itself. But there is a matrix that anti-commutes with the Hamiltonian. And that means, just like in the model, like the SSH model, there is a winding number that one can define. And that winding number actually changes as you go across the Brillouin zone. If I go to the other, it changes in these lobes of the nodes. So that winding number, for example, is shown here. It's 1 in these wings, and then -1 in these wings, is 0 everywhere else. And indeed, if I look at the system with open boundary conditions, I will find bound states exactly in those lobes. Okay. So these are known as drumhead surface states of these nodal lines. All right, so let's speed through. I want to talk about, this is a very recent work. For details, you can consult these archive postings. But there is a conceptual problem, especially on the fundamental side. When you break Lorentz symmetry, what is, because now the actually appears to be observer dependent, right? Because if I boost, for example, from one observer to another, then the energy spectrum changes. The energy spectrum is not Lorentz invariant anymore. So this leads to what is known as a concordance problem. So I'm going to take again the B term, and a concordant frame is one in which B is basically smaller, much smaller than M. So in this perturbative regime, then there is no problem. Sort of when you boost, of course, the energy spectrum changes. But for example, no positive energy will go to a negative. So, okay, so this is called a concordant frame. So the physics appears to be consistent across these frames. But what happens if we are in some situation where B is much larger than M, or mathematically, you can just take the limit of M going to 0. So in this ultra-relativistic or relativistic limit, B is always larger than M. So now you have a problem. Any boost basically takes you to a non-concordant frame. Or physically, you might wonder, if I'm an observer and I'm observing, and I am now boosted, because of whatever reason, what is the consistent physics that between these two frames? Okay, so here's sort of how we will go about thinking about this. So these are energy bands. You can think of this as basically like relativistic quantum mechanics or single particle physics. If you want to think about the vacuum, you have to actually do many-body physics or do quantum field theory. And the way that you would translate between these two is you take the sort of the lower cones here and flip them over there, and take this one and flip it over here, and then you end up with these two cones. Okay? So these describe particles and antiparticles. In condensed matter, you would think of filling up these bands, say up to some Fermi energy, and then particles and holes are described by whether these states are filled or not filled. All right. I think I don't have enough time to go over this, so I sort of hinted at this. This is an interesting case when you have an interesting example. When you have Lorentz violation, you can have unconventional processes that become possible. So for example, this unconventional pair production. In the original frame, let's say your energy spectrum looks like this. You can come in with an electron, and that can decompose into an electron and an electron-positron pair. And as you can see here, these energies and momenta have to be very low to actually by the energy momentum conservation. But if you go to a highly boosted, this is drastically boosted. That's the beta value. But in that, this process actually looks like energy and momentum scales. That's kind of an interesting thing that you should be able to observe in those frames. Okay? So does this happen? So that's basically one of the aspects of the concordance problem. Is this real physics? Go through this. So this is a previously proposed solution to this problem. It's mathematically rigorous and interesting. Basically, the upshot is that you define some kind of positivity region, so that these are the bands that you would consider for building up your quantum field theory. The one thing we should mention is that in many cases, these bands can be nicely separated. But in some cases, they are intersecting. So your positivity region actually goes through these points, and that might lead to some non-analytic behavior. All right, so this is really and various methods or various approaches have been proposed. So one, for example, is to just reject non-concordant frames. Just say, I will do my physics always in concordant frames. Okay, there's a set of concordant frames, possibly. And this is physically motivated because, of course, as I said, many tests show that these coefficients are, upper-bounded and vanishingly small in our frame, which itself is boosted not very highly with respect to, say, the sun-centered frame, and the sun-centered frame itself is not boosted very highly with respect to the, this galactic frame and so on. So maybe this is a good assumption. Okay? And of course, in fundamental physics, we are not in the ultra-relativistic limit, so this is nice. But conceptually, it's very restrictive. It basically throws away all these other frames and, restricts the physics. The other, for example, the positive energy criteria, this is mathematically motivated. But of course, then it means that the vacuum is not unique, which may be fine, but we don't exactly know how, how to choose the frame. Okay? So I would say that a full resolution, in this sort of our point of view, should basically do these three things. So it holds for any for large Lorentz violation, or in other words, in highly boosted frames. And it should be applicable to interacting fields. So the physical solution, let me go through this quickly. The connection, inspiration comes from the fact that while semimetals have the same effective field theory as these standard model extensions, and they have a ground state. And so there's a physical ground state, and that doesn't have any problem if you boost it or not. I mean, you basically take that ground state and describe it. You can describe it in any frame you want. That's just a frame or a coordinate transformation. And the perspective here is that the similar thing should happen, or the similar approach can be taken on the fundamental side. Okay. But how is that ground state chosen? In a Weil semimetal, it is determined through the interaction with the bath. The bath, of course, it could be phonons, photons, whatever degrees of freedom the electrons are interacting with. But that gives us basically a physical framework for describing the vacuum. Right. So let me just say this. So you can add a bath, for example. So this is a toy model. You can take the ultra-relativistic limit, add a bath. Let's say it's a real scalar field. There's some coupling. But whatever this generic model of coupling is, it should satisfy the thermodynamic conditions of equilibrium between the fermions and the bath. And that means, for example, that the chemical potentials should be equal. So taking the bath to be a real scalar, that means the chemical potential is 0. This is massless as well. And that sets the Fermi energy of the fermions also to be at 0. So if you're sitting in a frame where the bath is at rest, then the Fermi energy is here. And indeed, there will be a density of particles and antiparticles in the vacuum in that frame. Of course, the question is, how do you choose the bath? What is the bath, right? And there, you really need physical input. You might argue, for example, it could be the cosmic microwave background coming from the early universe expansion and so on. But that's where the physics needs to come in. So you cannot do this approach without at least some physical input. Just like in the Weil semimetals, you also need an environment. And that environment is whatever the degrees of freedom are that the fermions are coupled to. So let me go quickly to this slide, because I want to talk about this very briefly, about how you restore concordance, or how you solve the concordance problem. So for example, if you go to a highly boosted frame, then the bath that was determining the vacuum now itself is moving in this frame, right? So I need to do relativistic thermodynamics, or relativistic statistical mechanics, and the probability factors take this form. So there is some scalar temperature, scalar chemical potential. These are determined in the rest frame of the bath. But now in this frame, the bath is moving, and I have to use this for velocity and for vector, for momentum. And if you do a little rewriting of this, you can write it in this way. And you can see now that the interpretation that this quantity, mu minus v dot p, is a chemical potential. It gives rise to this tilted sort of Fermi level, kind of comes out of this. The difference is that these quantities like v, mu, t, and so on, these are really thermodynamic variables that are determined through the equilibrium with the bath. So I'm going to stop here. I'm way over time, I think. But you can find details of this. So there are two papers. One is the sort of addresses the conceptual problems, and the second paper actually does a detailed calculation of how you set up the quantum field theory in a coordinate invariant or in an observer covariant way. Yeah. Okay. Thank you.
Well, now we are over time, but we have just time for one quickly question.
So for your assessment of the concordance problem, this old question about the B being time-like, space-like in the context of QFTs, and whether you will have consistency or not, is
Right.
that important for your
Yes, so our answer is that there is a consistent approach. And so, you know, but you need additional input, additional
right.
physical input. So in this perspective, once you have chosen the bath has a rest frame. You can determine the vacuum, you know, using usual sort of textbook statistical mechanics in that frame. And in any other frame, you basically are doing a coordinate transformation. But you can also do that in the other frame if you want, except the bath itself is moving. So for example, it has a non-zero center of mass velocity, and that velocity itself is a thermodynamic variable that has to be matched with the velocity of the system as well. But yeah, so the answer is you may end up in boosted frames, for example, to see, the observer will see, say, a density of particles or antiparticles emerging sort of, I guess, spiritually similar to, for example, the Unruh effect, right? But in the Unruh effect, you're breaking Lorentz symmetry by accelerating. Here, Lorentz symmetry is already broken in the action.
So let's thank again Professor
Thank you.
Babak.
You probably need this.
I'm sorry. Aquí está. Abre esa, por favor. No, esa, la de arriba. La de arriba, esa. Y saca el PDF, ¿dónde está? ¿PDF? Sí. Es este, ¿no? PDF. A ver, este. Debe ser este, ¿verdad? Arriba, arriba, arriba. No, ese no, ese no. Este. A ver. Cinco.
Now we are going to continue with Professor Castaños from the Institute of Nuclear Science. So go ahead, please.
Well, first of all, I want to thank the organizers for this invitation. And so I am going to present this, how to determine these magic angles by means of quantum information concepts. In reality, I will try to communicate only one idea, then my talk. It was mentioned previously in this week, This work ¿sirve esto? This work was done with Manuel Calixto from the University of Granada and Alberto Mayorgas. He was a former PhD. He got the PhD the last year. And this work that I am going to talk it was submitted to Physica E, low-dimensional system and nanostructures. Let me see. Oh. Well. Go ahead. Thank you. Motivation is, I can add all the talks that I have here, but for me it's an example of a large class of two-dimensional crystals, which can be extracted from layered three-dimensional materials or grown artificially. For example, epitaxial growing on the surface of silicon carbide. It was isolated for the first time in 2004. It has been mentioned before. And graphene is a gated semiconductor whose valence and conduction is touched, providing a research tool to investigate QED and bring it to other issues of condensed matter and particle physics, as we have seen in this meeting. Two-dimensional crystals can be assembled in three-dimensional structures that do not exist in nature and have tailored properties. Some of the speakers mentioned that. What is the twisted bilayer graphene? It's a graphene sheet on top of the other graphene sheet with a twist angle. And there are mainly two types of stackings. They are called AA and AB, or Bernal. In this talk, we are concentrated on this, the AB stacking. In the predictions with this, I am using the Hamiltonian of Bistritz and McDonald, or my interpretation of the Hamiltonian of this and McDonald. Predictions for a discrete set of magic angles, the effective velocity vanishes. The lowest Moiré band flattens, and the density of states, together with the flow conductivity, are strongly enhanced. These are results of this work. Yes? The objective of the talk is to convince you that by considering the BM, I am going to call it BM model Hamiltonian, to demonstrate that the following measures can determine the magic angles of the twisted bilayer graphene by an angle theta. I am using this concept, the fidelity. It was mentioned by David, but I am considering the theta as a control parameter or parameter. If we are going to consider only the first conduction state, the first state of the conduction band, I am going to call it psi 0 mass, plus, I'm sorry. And the last state of the valence band, psi 0 minus. And the fidelity, then here I am assuming that the theta is a continuous parameter. It seems that experimentally they can construct bilayers with many angles. Then this is the overlap, the standard that one knows in quantum mechanics. And this is the fidelity in our definition. And you can use also the overlap between the conduction and valence band. You will get information. In the limit, with this delta theta goes to 0, this goes to 1, and this goes to 0. But these are important quantities, and you will see how we determine the. We also use the hopping probability between the layers. This is related with the non-diagonal terms of the reduced density matrix. And finally, I will mention the entanglement measures between the layers of graphene. We use two different measures. The linear entropy, that is related with the trace of the reduced density matrix square. And this parameter beta is M that is defined in this paper. And is related with the correlations that you have two systems that can have N1 and 2 degrees of freedom. Yeah. The magic angles are obtained when there is a sudden change in the structure of the corresponding wave function. No? So, yes. Then here we are analyzing the structure of these valence and conduction states. And here the same. I can say I am analyzing the behavior of this with this wave function. The monolayer graphene was discovered in 2004. And high-quality sheets of graphene on different substrates have been produced through the procedure of micromechanical cleavage of graphite. Each atom carbon has 4 valence electrons, 3 forming the hybrid sp2, and the other delocalized in a p orbital. The hybridization between the orbitals S and P leads to a plane trigonal structure. And in the, I am using the nearest neighbor type Weyner approximation to describe it. Well, this is the distance that was mentioned before also between carbon and carbon. This is the constant of the lattice, and this is the real values of in the real space and the reciprocal space. Experimentally, the bilayer graphene has been obtained with this distance between the layers. I mentioned again these two types of stacking. No? We are going to consider this is, according to the literature, is more stable and energetically preferred. The Hamiltonian consists of 3 terms. I am going to this twisted bilayer. Then 2 single layer Dirac terms, this one in the linear approximation, and a tunnel term described the hopping between the layers. The important part is that you have 3 momentum transfer vectors that are called, this Q will be the expansion around the cap point. Yes. Then is Q bottom, Q tunneling to the right and Q tunneling to the left. This is the Hamiltonian. This is the Fermi velocity. Then in principle, we have all the parameters are known. No? The Fermi velocity is taken in this form. It is taken in this form because recently, experimentally, was determined this magic angle. It's the only one that has been determined, certainly, 1.1. And there are 2 papers related with us in the laboratory of Jarrillo, that is in Spain. And the spin or Hamiltonian acts on the individual I and B triangular sublattices, degrees of freedom. This is the distance carbon-carbon. This relation between these parameters that was mentioned in the last talk are important, the intraband energy and interband energy that I will mention in a moment. This is the tunnel interaction, no? In the low energy continuum model. No? We have this values, no, the momentum, no, is Q plus this QB, Q plus Q3, the translations, and so on. These are related with this K theta. Yes. And all of this, the magnitude of this are given by this, the magnitude of this K theta. This K theta has the angle of twist. Yes. And the interaction terms associated to the hopping between the layers is given by these three quantities. No? Yeah. In the Dirac point, I am going only the Dirac point K. This is omega, that is W, double B, is, has this value. And again, this is taken from the paper. And these are, this will be very important because this, in this, I am plotting the momenta in the direction x and y, yes, divided by chi theta. And you see here is the one layer. This is the second layer. This is the first layer, and so on. And this is, with this you can construct the Hamiltonian. In reality, this is related. You remember this will be QB, Q to left, or Q to TR. No? This gives you the radius of this R1, square root of 3, 2, square root of 7, 3. And this determines the Hamiltonian matrices of sizes 8, 20, 26, 20, 50. For example, this appears in several papers. For the case of d equal to 8, one has the Hamiltonian. You see, this is the one layer, and the second layer is divided in 3. The 3 points that I mentioned before. No? And these are the connection. These are 2 by 2 matrices. And this is and this is the situation in the momentum space and Hilbert space basis. How to determine? No? You have these are the blue and red is the in the spatial in the rotation is the same in the reciprocal lattice and this is the normal one in the reciprocal lattice, and this is the Moret that is called. When you have these two layers, all the time that you have two periodic systems and you put one on top of other, appears these Moret patterns. Yes, when you twist it, appears Moret patterns. That it was shown by Baba that you can have the same structure, the same type of lattice, but a large distance in the real space. But that is the reason that you will have a super lattice, super Moret lattice, or mini Moret lattice. Mini Moret lattice is this one. And it's very important because we are going to study the behavior around this point, the point K, but in the Moret, in the mini Moret lattice. And then we will go to this point, we will go to the gamma point, we will go to the M point, and we return to see this density of states, the spectra. See? What else is? Okay. Then, Hilbert-based states. One can define this momentum, no? I call it momentum or wave vector. It's momentum, this L denotes the layer, and this M is a two-dimensional space that given by integers, no, positive and negative, and these are the state. Then the set of orthonormal base states, you have this one, L, you have the values of this vector M, of these two values of the integers M1, M2. Yes, and this is related with the triangular sublattices of the graphene, and we define it in this form. This Q is the momentum. S this A bit, and with the spin down and up. And these states are orthonormal, no? And this is in this. You can find it in this work of Katarina. And there is also something in this thesis. And this is the radius. The size of the truncated Hamiltonian matrix depends on the number of higher order nearest neighbors. Yeah, on the models of the wave vectors, we call it RR, depends of the layer that you have, and is divided by k theta, and this is the result. It's interesting that this is related with the number theory, and maybe it's important because you have distant possibilities to take M1, M2, no? For example, here M1 positive, negative, no? Then you have the standard Lockean number on positive, negative, and so on, no? And here is the important point. The important point is that this quantity defines an ellipsis in this M1 plane, in the M1, M2 plane, and I am going to use it to define the size of the Hilbert space. Again, I put it. In reality, you have these two layers. You have the blue and the red, yes? If you see the form of the wave or the momenta, no? In one layer or the other, they define two ellipses, but they are not there. They do not coincide. But to simplify, we are going to use only the same values. No, you have these black dots are formed coincide. There is it can be red or black or blue. No, red or blue, and this number in this example, in this figure, tells you the size that you have in there. Then this ellipsis has this, no? Black color, okay. Now, the matrix elements, this is the standard Hamiltonian for each layer, and this is the tunneling that has three terms: the behavior of the momenta to the left part, to the right part, and to the bottom. Yes, and next, I mentioned before that I am going to study this transition and calculate the density of states for different twist angles. This figure was shown by Baba. Is this the same? This is 5 degrees. You see, this is the structure. If you consider only the bilayer graphene, you will have almost this result. No? Is the result. However, when you put this angle, that is 1.05 in our calculation, you have this, and the density of states is enhanced around the zero, no? The zero value. And this is the behavior. Here are only the states of the point K. That is the reason that we start in Km and did this path that I mentioned before. And the size of this path, you see, when theta is lower than 1 degree, is going smaller and smaller. That is the reason that if you keep only this 4x4, 8x8 Hamiltonian, is not enough. You need to take the other shell, the other shell, the other shell. Sorry. Well, here is an interesting phenomenon that you can study in these magic angles is the Van Hoff. And Van Hoff, again, is related with this critical behavior. I am not going to study now, but mention only. This is another angle, you see. You see how this density of states increase, no? For these angles. Again, see? We are only interested to this one, no? The closest to 0. Then in previous figures, the low energy flat bands at magic angles are these ones. This is not new. This is, I am reproducing the results. You see, these are the results. And this, for the density of states, we use this, when a Lorentzian. The convergence is this. All the calculations were done with the size of these Hamiltonian matrices. And this is like a hand rule, you see. To get convergence is related with the square of 10 divided by the angle. And if the angle is very small, like in this case, you need this. No? Size. For the other, not. For this, not. How we calculate the effective Fermi velocity? Well, we use this relation in 0. We divided this V small is the original Fermi velocity, and this is the effective Fermi velocity for the again the first conduction band, first state of the conduction band, and the last state of the valence band. No? And we evaluated in Q equal to 0 to start in the K point. Then vanishing at angles, magic angles, no? The effective derived velocity vanishes at magic angles similar to the ones in the literature. And this is given by this. Note that their particular values are sensitive to the choice Hamiltonian parameters like the Fermi velocity, E, and or BF is the same because, and the Hoping energy, omega. Then the information markers, no? I remind you, this is for pure states, this is the overlap, no? States normalized. And this is related with the fidelity that I mentioned at the beginning, no? We expect sudden drops and this, no? And if you want, you can use also the fidelity susceptibility. That is, sometimes this is easier to see the results. And you see the fidelity turns out to be a good marker, precursor of a quantum phase transition, even for finite size systems near a critical point. In the literature, when you have a quantum phase transition for a finite system, you call it precursor. In reality, for me, is a sudden change in the structure of the wave function. Normally, it's the ground state wave function. In here will be the change in the first state of the conduction band and last state of the valence band. Well, next. And here are the results, no? In here you have three graphs, no? This is the Fermi velocity these points are 0. These 1, 2, 3, 4, 5. No? This is the magic angles that are reported in the literature. But we found this, that it seems, we call it anomalous, but it's not in the graphs that in the papers. But we know what is going on in this here. But I want to enhance that. You see, this point, you can see it with this fidelity of the conduction of the valence and conduction bands. There are two types of lines here, blue and red. And you see here is marked, here is marked, here is marked, here is marked. This is marked. No? I am telling that this is not a magic angle, but something is happening. And here is a magic angle, and a magic angle, and also here. But you can also, with the overlap of the valence and conduction, for me it's interesting also to this quantity, no, this one, the overlap between the conduction and valence states, because you see here, in this point, has a large fidelity. Then if you put this delta theta that I put equal to 0, they must be orthogonal. But you change a little bit, and you see that they have a lot of components equal. No? And here is detecting. No? I put this one to understand this point, and this is, we go to this. I need to tell that I am concentrated in small angles, not large angles. Yes, because then this is the step that we use to calculate these results. And this inset that we put here is to understand that this is related with this quasi-degeneracy. You see, here you see blue and red are the states that I mentioned before, the first states of conduction and valence, but also the second. No? You see here, if you calculate the Fermi velocity, you will have this, you have 0. Then you have 0 also for you can call excited states. You have a 0 conduction. Well, this is, but for me, this anomalous, I didn't like, but we mentioned anomalous because it doesn't appear in the calculation, no, in the other. But we can explain it. I hope this combines it. The entanglement. Well, I put this because the word entanglement was introduced by Schrödinger in 1935, and is in response to the EPR article. And it says, this translation, I took it from here, from this. No? The essence of entanglement. This was a book in honor to Clauser. No? It says, maximal knowledge of a total system does not necessarily include total knowledge of its parts, not even when these are fully separated from each other, and at the moment are not influencing each other at all. But that we use, or the people use quantum information theory, because you want to have maximum entanglement, because when you measure one of the parts, for example, if you have a composite system, when you measure one part, you gain a lot of information. Yes? Then you know the complete system, but not the behavior of those. But yes, of the components. For pure states, the entanglement properties can be studied by this von Neumann entropy, that's called entanglement entropy, or equivalently the linear entropy given by this. And this is the other, no? The other form that you can write a general composite density matrix. These are the unit, the unit matrix of 2 by 2, and these are the standard Pauli matrices in the sector 1. In the sector 2 is the entity and the opposite, and this is the correlation matrix, and these are well known in quantum optics. Is the polarization vector, and here I'm indicating the subsystems A and B, no? A and B, for example, no? This row A and B is a composite system. And well, you define this matrix. You see, if this is 0, well, this is not, I'm sorry, this is a correlation. You define in this form. This is a correlation between the two sectors, and this is related with this separate sector. And you can, for this case, 2 by 2, this is the trace, the beta, and beta is bounded, and you have the information. Then, this is, for example, I put this example because you can evaluate, you can determine all analytically. No? And this is the bilayer graphene with the Bernal stacking, and you have this form. This, in reality, you remember the previous that you have three hopping transitions. But for this case, that you make the twist, because in the Bernal stacking you move and rotate. You move to put the atom ISO rotate. Yes, and the twist. But here is you only move in that direction, and you will have this is related with 3 times the W that was before. And this, you can solve it. It has 4 energies. These are the energies. These are the wave functions. You can define this dimensionless parameter, eta, related with, again, with the Fermi velocity, the momentum, the magnitude of the momentum, and the vertical tunneling, because it's A over B. And this gives me, for the values that we use, 3.83, the magnitude of Q. And it's measured in nanometers to the -1. You have this one, no? And this plus minus reference again, the conduction and valence bands. The coefficients of the wave functions, you can write it in this form. This is the Hilbert space, the layer, and the triangular lattice. Then the density matrix, you can write it in this form. In reality, it's independent of this n. This is to put 1 and 2. Yes, and then this is the reduced density matrix, no? And to see, you calculate the linear entangle and the von Neumann entropy, the linear entropy and the von Neumann entropy. These are the eigenvalues of the Hamiltonian. And you see, this is the interesting, is the maximum entanglement entropy you obtain in the that is in the linear case 1/2 at the Dirac point when Q is equal to 0. But if this Q is larger, then the states are almost uncorrelated, no? Far from the Dirac point. In the validity of the model. 5 minutes? Well, for the general case, I remember this D is 2n, related with the layers and the space, the A, B, and M1, M2. And then, sorry. This is the wave function in general. Then you can, this is the reduced density matrix. You have it here, no? Then you can evaluate again the linear, and we evaluate only the linear entropy, see? And the results. Then for the closest valence eigenstate, we calculate this. Well, it's only to see the behavior of these quantities that I mentioned before, yes, in the same trajectory. Let me skip this because, and here is the hopping probability, okay? And you see again the angles you can determine, no? Exactly. The interesting that this hopping probability doesn't is this in 0.5 is very small, but it's there. This is the linear entropy for the problem, and you see again the changes when you take the derivative to see, and you find the results. This is the nicest. Maybe that's the reason that I mentioned only this. Similar results for the closed energies. This was done for the valence states, but similar results for the conduction states. This is the nice form to learn how to evaluate the entanglement when you have a large system. This is 2n. And then here you have, you remember we have Pauli, no? Here we have Pauli, and we have the generalized Bloch-Gelman matrices, no? Associated to the SUN group, no? You define, again, this correlation. In this case, the matrix is not quadratic, square. Is this dimension? And this is the measure. Then, again, you have this only to remember the definition, but you can construct this in general. This matrix only with the structure constant of the group, and this is the result. You see. This is more complicated to calculate than the previous one. The previous one was that was the reason that we used this ellipse to put in only m's equal for the red layers. This is more difficult. That's the reason we stop here. No? This is the radius that we took. But you see, you find the same results. Well. These conclusions, no? Sorry for this. For a small twist regime, we have found that the linear entropy of the reduced density matrix and the Lins-Mahler beta parameter allows to determine the magic angles of the twisted bilayer graphene. This means that in that point, the layers of graphene are strongly correlated. The fidelity and quantum correlation of the first conduction band eigenstate is also can detect the magic angles, and it seems important to integrate dimensional information theory markers to study other effective Hamiltonian systems in topologic materials as a complement to establish properties of three-dimensional topologic materials, for example. And this is the angle that we found that is related with the vanishing, but for first excited conduction states. And the important point is to study this. Yes. This I mentioned before because we took that all the parameters fixed, you see, but it seems that it depends of the epitaxial graphene. Some of the values can change, mainly this one, this double B. But they said that it can change by the 7%. Then you see we did it, and then there is not a large change in the structure of all the quantities that we calculate. But well, so I finish here.
Questions?
Thank you very much for a very interesting talk. I like it very much. I have maybe two questions. The first one is that, do you have an explanation why the entanglement changes from its maximum for the Dirac cone, and I think it's less for the gamma point? If you have...
Yes. Let me put it there.
Because just a comment that for the magic angle, the analytic expressions for the wave functions are not for the other angle, but just for the magic angle, and they are given that.
This is interesting because you see here, you are telling this, no? These are the, you see, the Lyell probability is 1/2. Then is the matrix is 1/2. Then it means in the 2x2 system that is completely entangled. But this is not happening outside. You see, also this is, we take this like a limit, 10 degrees, no, that you lost all the things, no. But maybe you see these lines maybe answer your question.
Yeah, but my question is more like physically, what does it mean? I mean for why that is reciprocal. So what happened for the wave function?
Happened?
Yeah.
Well,
more than.
Well, the density matrix is the reduced density matrix of the layers, you see, and then give you all the information that you want. It gives you the information of the probability to find the electron in the layer 1 or the layer 2, and
I was thinking more like
diagonal terms.
Okay.
Tells you about the transition between the two.
Yeah, I was thinking because there is an invariant on the K point. There is an invariant that you can prove it, that there is an invariant. Yeah, that's why. I will show you. We'll have in our work.
I don't know,
but
thank you.
Yeah, but this is very interesting because somehow it seems to be related with the, and the other, can I ask just a technical question? When you have a flat band, you have a massive degeneration. Do you need to, you just take the density matrix of each state, but not of the?
Yes, we define only the, as I mentioned, one state, the first state, the lowest state in the conduction band, and the highest state on the valence bands, and that's all. Because we have a finite system, and we determine the changes are included.
But when you go to a magic angle, they degenerate.
Yes.
And it doesn't. Okay.
I don't know.
No, my question is that you have degeneration, so you can change the basis and.
Well, in reality, we don't see if it's exact degeneration. Because you see here, we are using, let me.
Oh yeah, because you are working with something that's called the non-chiral model, because you have a 0.8. Because in the chiral model, okay, it's okay. Yeah, you solved my question already. Thank you.
Well, maybe but
Is there another short question?
Like, if I understood correctly, like this is like the test like the entanglement and all of the properties you are studying are zero temperature, like.
sí. Yes.
So like,
yes.
do you know what happens if like the wave functions have to be like the individual wave functions have to be replaced by a density matrix, like whether it? Yeah, I don't know. Like,
No, we haven't done to replace the state. for
yeah,
it?
with some thermal, like.
No, we haven't done that.
Okay, thanks.
In this case, we have done in another case with temperature. Putting this Maxwell-Boltzmann by hand, and you keep it. You conserve this type of things, but we haven't done in this case.
Okay, so like some signatures, like.
Some signatures, I think, remain.
Octavio, what is the connection of the ellipses that you show with the equation? I lost the point. I'm so sorry.
Because the states, you have we are considering the free electron is one body.
Yes.
Yes, the free electron. Then the free electron is given in terms of the moment. And the moment is given in terms of these M1, M2 that are integer numbers.
Yeah, but you show an equation, right?
Yes.
With M and N.
You want to. It's the opposite. Sorry, boy. This one. This is the matrix element, and the state is
Yes, that equation.
the other
Okay.
one.
Okay.
This is the state, you see, here. This is the layer, and this is the point that you are. We are going to take it 0 and QLM, yes? And this QLM depends of the M1 and M2. And these three vectors, this is transfer vectors. These are important, that this has the symmetry of the triangular sublattice.
Okay, let's thank to Professor Octavio.
Así se queda, ¿no? Ya. Perdón, ya me lo llevaba a mi casa.
Sí, de recuerdo.
Sí.
¿Quieres que te avises 5 minutos antes de los 40? Sí.
El bolsillo, la cintura no sé.
Sí.
Ahorita está encendido, yo le subo volumen cuando vaya a empezar.
Ah, ok. Sale. Perfecto. Muchas gracias. Tengo el mío aquí.
There is one announcement. After the coffee break, please don't introduce coffee to the auditorium. Okay. So we are going to continue with the presentation of the Professor Thomas Steckman from the Institute of Physical Science. Please.
Okay, yeah. Thank you very much, Pavel, for the introduction, and thank you to all the organizers for the invitation to this wonderful event, to give the opportunity to present a bit on our work on how to control the current flow in 2D materials. I will discuss two different approaches, two different systems here. Let us start directly with the first one. This is with calcular graphene. So what is calcular graphene? Well, it's very much at the heart of these ideas of August Kekuli for the benzene molecule, whereas you have this alternating double and single bonds. So here, for example, we have a small nanoribbon of graphene, of Kekuli graphene, where you see here just this hexagon, and the idea is that we have here these black bonds, these are the single bonds, and the red bonds, these are the double bonds. So this one here is the, let's say, original idea of Auguste Kekule for the benzene molecule. And the idea is to realize structures like that here in graphene. There are different patterns of, do you hear me well? I hear some back reflection of my, yes? Okay. So this pattern is called also Kekule-O graphene, as there are different types of Kekule graphene, Kekule-Y graphene, or Y graphene, Kekule-M graphene. So we will focus here just on Kekule-O graphene, where we have this O-type structure here of these bond alternations. And when you introduce this here in graphene, you get a much larger unit cell. So the unit cell is this purple rectangle here. You see here we have a unmodified carbon hexagon, and then we have two modified carbon hexagons, and then there's coming again an unmodified carbon hexagon. So this is a unit cell, and when you do this, what is happening, the Dirac cones at the K point, they are mapped in this system to the center of the Brillouin zone, to the gamma point. They're both mapped to the gamma point, and there is opening a band gap here of size delta. Delta is just the difference in the hoppings, the difference between the single and the double bonds here in Kekule graphene. Has it been realized experimentally? Yes, there are some few experiments, for example, here with bilayer graphene with lithium atoms intercalations. So we have here these two layers of graphene with lithium atoms in between, and they made here a photograph of with atomic force microscope and saw here these bond alternations in the pattern, and they measured also here the band structure of the system, and they saw here these degenerate cones with a band gap just at the gamma point. Yeah, so I'm here at a workshop on topological quantum systems. While you might agree that this is a quantum system here, I will describe it by Hamiltonian. Is it topological? No. Kekule-O graphene is at this point not topological. When you evaluate there these numbers like the Chern number, the Berry phase, you get zero. So the material at all is not is not a topological quantum system. But nevertheless, what we did here, we took two parts of these systems with a grain boundary. So here, this is the unit cell which I saw you on the slide before here. And this one here in this right part of the system, I just take this unit cell and I pull it by one carbon hexagon downwards. In this sense, we have here a grain boundary just here at this dashed vertical line here. And what we did then is we study the current flow in the system. As I mentioned in the title of my talk, we study the electronic transport properties of these materials. So we put here two contacts just at the boundaries of the system. And technically what we apply then is this Green's function method to evaluate here the current flow in the system. I will not go here into any details, just study here the result. This one here, this is the current density. So the red current color shading here is the current density of electrons which are injected here. It's a bottom contact and flowing here to the top contact. You see here a very located current flow pattern just here at the interface here of the system at the grain boundary. This one here is the local density of states. So we see here just a state located at the interface. These ones here, this is the density of states induced by the metallic contacts which we have here at the bottom and at the top. And this one here, this is the transmission or the conductance as a function of the electron energy. And yeah, maybe we focus first here on this black curve. This is just calculographene. And what we see here, well, there is zero conductance here in the range, in some energy range. This is just the band gap of the system. No, there is zero transport within the band gap, and then when we pass through the band gap, then the transport here ramps up. So with just calculographene, it's not very interesting. But here, when we have this grain boundary, this is the blue curve, then we get these additional plateaus of one conductance quantum here in this energy range. So we have still a smaller band gap, but we have also these conductance plateaus here of ballistic transport here of the electrons from the bottom to the top contact, which we saw already here in these two figures here. I forgot to tell that this current density is evaluated just here at the energy region here of this plateau. Okay, and we can make also different patterns of this grain boundary. Here we oriented the grain boundary in the horizontal direction, and we see the current flowing here from the left to the right. Here we made a grain boundary in this corner shape, and the current flows here from the bottom edge to the left edge. And we also made here this complicated pattern here with the letters of or institute, where the current is injected here at the left edge, and it is flowing here in this complicated way here through the system. So with these grain boundaries, or in other words, by engineering these calculi distortions in graphene, we can control here the direction of the current flow. And these states are not one-directional, they are two-directional. If I would inject here the current here at the left edge, it would go just with the arrows pointing in the opposite direction here from the left edge to the bottom contact. So there's no one-way transport in this way, but these states, the current which is flowing here is rather robust against disorder. So what we did here is we randomly changed here the bonds in the system. So we broke somehow this perfect calculi pattern. We switched randomly bonds, and I think up to 20% of the bonds, and evaluated again here the transmission and found that these plateaus are rather robust against imperfections of the lattice. Okay, how can we understand this state localized at the boundary, at the grain boundary here, which we call also here soliton? Well, we took here this Hamiltonian, this low energy Hamiltonian of calculographene, which has this form here. So this one here, this is a mass term m gamma, which opens the band gap of the cones at the gamma point. And this term m gamma here has this form here. So this effective mass of the electrons in calculographene has this form. And this, you see here that there is a complex phase, e to the I gamma. And when we have just calculographene, you can choose gamma to 0, and well, this is then just 1, and we have a positive mass here. So with this parameter gamma, I did not put here the equation. With the parameter gamma, you can control here this calculate pattern. But when we have now here this grain boundary, well, we can choose in one region gamma to 0. But then in the other region, we have not the flexibility to choose again gamma to 0, so we have to choose another value to generate this calculate pattern here. And it turns out to generate this grain boundary, we have to choose here this parameter gamma 2 pi over 3. So effectively, the electrons have here a positive effective mass, and here in the right region, they have a complex effective mass. And this this difference between these two regions generates then the soliton here at the grain boundary. So we made here an ansatz for the soliton, which is localized just at the grain boundary of two regions, no? Of where to the left, the electrons have a positive effective mass, and to the right, they have a complex effective mass. And which in this sense is also known as this Jakiv-Rebbe model, which was already introduced on Monday evening, where they deal with two regions where the electrons have in one region a positive mass and in the other region a negative electron mass. Here we have a generalized Jakiv-Rebbe model in the way that we have a positive mass in one region and a complex electron mass in the other region. And making then an ansatz for the soliton, we obtained here the energy band of the soliton, and this is the band structure here. In blue you have the numerical calculated energy bands of this system of Kekule O with a grain boundary. In green, the green curve here, this is the energy band here of the low energy Hamiltonian. So of this Hamiltonian you get this energy band. So this is this one here, which agrees perfectly with the numerical calculated band structure. And this red dashed curve, this is just this expression. So this one here is the soliton. This is a state which is localized just at the grain boundary. So we understood now the origin of this soliton. I mentioned at the beginning, well, there is at least one experiment where they use lithium atoms to generate such structures. We did some more work here using DFT calculations on the realization of the systems, and here we used titanium atoms on top of graphene, and it can also be intercalated here between a graphene and a hexagonal boron nitrate substrate. So the short story is here with such an arrangement. So here you see graphene and these green dots, these are just the titanium atoms. You have in some energy regions, you have these localized solitons here in these systems. In other regions here they disappear, but there are known reasons why they disappear here in other regions, possibly because the titanium atoms are doing some more manipulations of the graphene systems. But these solitons, they exist here in the system in a rather broad energy range here. And with this I would like to conclude the first part of this talk, where I showed that we can guide the current through the system by the engineering of these Kekule O distortions. And this soliton is gapped, so you can switch it in principle by electrostatic gates. You can switch it on and off. And I showed you that you can realize it in principle by decorating graphene with titanium atoms. And the details can be found here in this paper. This is the first part of the talk, where again I had a system which at the beginning is not topological, and then I showed that by introducing this grain boundary it somehow becomes topological. I still do not really understand this in which sense, because when you speak on topological insulators, you name this, or you try to find a bulk boundary correspondence in the systems. But here with this grain boundary, you somehow introduce the system by matching two different systems. Then you introduce something topological. In the second part of the talk, I would like to, as I said, discuss different systems. This is twisted bilayer graphene, and not at magic angles, at an angle which is larger than the magic angle. And I will talk about edge state transport in the system. And yeah, again, I'm here in a workshop on topological quantum matter, and I will show you that it is claimed that this system and this regime, which I will show you, is topological, but in our opinion, it turns out that it has nothing to do with topology here. This is a system which is not topological at all. Okay, let's start. So we take here this graphene bilayer, this graphene double layer, one on top of the other, and starting with the AB stacking, and we start to twist it. Here, we start to twist it, and we get now this Moire interference pattern where you have here this AA stacking zones, and in between you have the AB and BA stacking zones, I think. Yeah. When we go here, you can see them also. Here's this AA and AB regions. Well, as I said, there have been many work on this system focusing on this magic angles where you observe highly correlated phases leading to superconductivity and mod insulating phases. And yeah, I will not go into this regime here. Our work has been motivated here by this experimental paper, where they talk on Moire band topology in twisted bilayer graphene. What they do here is they have this twisted bilayer graphene system, and they have a Hall geometry that they have different contacts here at the edges of the system. And they measure here the non-local resistance. This means they apply a current flow here between these terminals and measure the voltage drop along these terminals here. And then this is the result. Here they have the resistance as a function of the electron density or electron energy, if you like. And they have here, at some regions, they observe this very pronounced signal here, this very pronounced non-local signal, which indicates somehow that there is some edge transport going on in the system, leading here to a measurement here of a voltage drop here between these two terminals. Okay, and yeah, in the paper there is some theory. So they show here that in this system, this is bilayer graphene at an angle of 1.68 degree, and at this angle there are small band gaps here opening in the system. And they measure this non-local system just here in these band gaps. When you go to different angles, these band gaps disappear. And they explain, again, this rise of this non-local resistance here by the presence of these edge modes here, just inside, counter-propagating edge modes present here in the band gap of the system. Well, and as I showed you in the first part of the talk, we have some experience with transport calculations, transport measurements. So we decided to have a more closer look to the system to realize it in our computers. And so we started here, just the first step is to set up the system and to find the band gap. So here we have this is the real unit cell of the system at 1.69 degrees of twist angle. So this is a real unit cell. And first, to find the band gap, one typical approach is to optimize it first with molecular dynamics, as the system does not stay completely flat. This one here is the interlayer distance of the system, and you see here that in these AA regions, the distance between the two graphene layer increases. So there's some buckling introduced in the system. And then we use a typical tight binding Hamiltonian here for the system, where we have a bottom Hamiltonian, a top Hamiltonian, and here an interlayer Hamiltonian, which takes into account here the sigma and pi orbital interaction between the two planes. just go to the results here. This is the band structure of the system here. This is the band structure of the system. And yeah, we see here that there are band gaps with a size of about 20 millielectron volts, so they're not very large, opening in the system. This one here is the density of states, not just calculated here along this path in the Brillouin zone. No, this is the total density of states in the system. You see here this black curve. This is the system optimized by molecular dynamics, and there's opening here, this band gap. And you see also here when you don't do this optimization with molecular dynamics, you see here that there is no band gap. So it's essential to observe this band gap to take into account the buckling of the two graphene layers. Okay, then we found these band gaps, as also observed by others, and found in the experimental paper. And yeah, then we said, okay, then let's make nanoribbons of the system. So this one here was a bulk system, which is periodic in this direction and periodic in that direction here. And now we said, okay, let's make a nanoribbon of this. Here we took just 4 supercells. No? So it's a narrow nanoribbon in the sense that we have just 4 supercells or 4 unit cells. But from the other hand, this system contains about 50,000 atoms now, the unit cell of the nanoribbon, and you have to diagonalize the system for different values of k. And yeah, here's the result. Again, the band structure here is a function of momentum of the electrons, and indeed there are popping up some bands inside of the band gap. And the color shading here of the bands, this is the inverse participation ratio. So it indicates here when you have these red colored bands here, it indicates that they are somewhere localized in the system. So these bands here indeed are inside of the band gap and they are localized somewhere. Well, then we said, okay, let's have a look here at these states. This is what we did here. No, here we have these states at an energy of 70 millielectron volt. This is just this state here. And we see, well, it's localized here at the right edge of the system, while this state here is localized here at the left edge of the system. When we take these 2 states here, we see they are localized here in these 2 edges. And when we take here a state, this one here, we see it's not localized at all. So yes, there are some of these states showing up in the band gaps. They are localized at the edges. Okay, then we made transport calculations here. Here's the conductance as a function of the electron energy. And well, we found these states. We saw in the band structure that the states are dispersive. So it's not surprising that we now see conductance ramping up here in the band gaps. No? So here we have a conductance here peak, and here's another conductance peak in this. So yes, there is transport inside the gaps, and the transport is close to the conductance quantum here, indicating here that there are states flowing at the ballistic states flowing at the edges. We also evaluated here the local current flow in the system here at different energies, here at this energy here, and we see that the current is flowing here at the right edge. Here this is the density of the current, and here at the left edge of the system. So yeah, but we found that the current is actually flowing only at certain edges of the system. It's not flowing here on both edges of the system. And again, we inject here the current at the bottom contact, and it's flowing here at the right edge. And when we inject it here at the top contact, it is not flowing here at this edge. It's just flowing here on the same edge, in the same way, just with this opposite direction from the top to the bottom. So these are again 2-directional or bidirectional edge states, which are localized only at certain edges of the system. And yeah, with this we did non-local resistance calculations here with contacts here at the edges, and indeed we observe here a signal inside of these band gaps. But the magnitude of this signal very much depends on how you connect your contacts to the edges of the system. So here in this calculation, we applied a current here between contact 3 and 4 and measured the voltage between contact 1 and 2. And here we applied the current between contact 1 and 3 and measured the voltage drop between 2 and 4. And you see here the non-local resistance, this is the black curve, changes very much compared these figures here to Z figures here on the bottom. So the results depends very much on how you connect your sample to the yeah, and then we got a bit puzzled. We asked us, yeah, but when you look here at this unit cell of this system here, maybe I go back here. When you look here to the unit cell of this system, this is the Moer unit cell. This boundary here to the right edge, this boundary here looks very similar to the boundary here at the left edge of the unit cell. So we asked ourselves, so what is breaking the symmetry here between left and right edge of the system to localize the state just here, let's say, at this boundary and not at that boundary here? And yeah, what we did then is we made a larger nanoribbon here. This is just 5 unit cell wide nanoribbon. And then we put here some cookie cutters to cut out a nanoribbon, which is just 4 unit cells wide. And we moved this cookie cutter here along the system to change the atomic structure here at the edges of the system. And we see here, depending on how we cut the nanoribbon. So we see, depending on the exact atomic structure here of the edges, we see here in the band structure that they are migrating in and out edge localized states. No? So it depends very much on how you cut the system here. If you will observe an edge localized state, or if you will not observe them. And this is somehow the conclusion here of this work. Very recently we became aware here of this experiment where they demonstrate in just bilayer, in gapped bilayer graphene, where they show the edge dependence of non-local, of the transport in the system, where they demonstrate that with different shapes of the edges, they can induce here or enhance non-local transport, edge transport in the system. And we very much believe that this is the same effect here, that depending on the exact atomic shape of the edges, you can have in these systems dispersive states localized at the edges. Yeah. And with this one, I would like to come to the conclusions. Now we showed here that in twisted bilayer graphene, at this particular angle, we have 2 gaps opening, and in nanoribbons there are appearing these edge states, which again turn out to have nothing to do with topology. We again evaluated here the Chern number and Berry phase of these energy bands here, and just get 0 there. And but these edge states depend on the exact atomic shape of the edges, and there are not defect states in the sense that these states, as you see here, they are dispersive. They can carry the current ballistically along the edges of the system. but they are somehow induced by the roughness of the edges of the system. And yeah, the details can be found here in this paper. And I would like to thank all the collaborators, funding by Condensed and UNAM. And I would like to thank you for your attention.
Well, we have a lot of time for questions.
So thank you for a great talk. For the first part, I have a question and a comment. Maybe I'll wait until you get there. The question actually is, so you have these two domains, but you can actually form, I believe, 3 domains from this Kekule pattern.
Yep.
Have you looked at putting them all together? Because I think that would create the vortex that I also was talking about in my first talk. And I expect, I haven't looked at it very carefully, I expect that you would get these domain boundary states, but you should also get a vortex bound state. And I don't know exactly how, I guess the vortex bound state would be at 0 energy. So if you sit at some other energy, then it would not participate in the transport or anything like that. But it might be interesting to look at that. Yeah. So have you looked at the other domains, or that's the question?
We have looked at the other domains. No? So you are completely right. We have this choose of gamma 0, gamma 2 pi over 3, and then you can choose gamma minus 2 pi over 3. And we did a look at these edge states, and they do not change. You observe the same. But I think we did not have a look at 0 energy,
Right.
you said.
Okay.
And I also expected this vortex is showing up there, but we did not have a look
Right,
at this.
and I think that actually has to do with the topology of the system. The topology, you're right. All these, Chern number or Z2 topological invariant, all those things are 0. But this system, I think, is a higher order topological system, because the low energy Hamiltonian is basically the same as the square lattice model and so on. So there should be corner states or vortex bound states of this kind.
Okay, yeah. Thank you very much for the comment.
Another question? Well, I have a question. I was wondering in this Kekule graphene, if you can design these grain boundaries in such that more or less in the same comment as Babak was mentioned, to build emulated topological insulator. Because somehow, I mean, in the boundary, if I understand well, you have conducting states.
Yeah, just here at the interface, right?
Yes. I mean, do you think that this is a possible? I mean,
well, my understanding of the system is, yes, you make a topological insulator by matching these 2 patches of Kekule with a grain boundary. And you can match them in actually very different ways. What is important here is the global difference here between these gray shaded and white shaded regions that you have there, this grain boundary, to induce this solitonic state in the system. I don't know if I understood correctly your question and if I answered it.
No, that's correct. I mean,
okay.
Another question? Well, if there is if not another question, let's thank to Thomas, please. And we can go to the coffee break.
Ah, fui mal.